Hi, so for this one, it says Seth has two retirement benefit options. Okay. And what's happening is that we want to. So it says the first option is to receive a lump sum of this amount, and the second option is to receive monthly payments of 25 years starting 1 month after retirement for the first year, and so on and so forth. Okay, and determine which of the following is true. So it seems like we have to compare these two scenarios. We have to solve whatever's happening here and compare it to a lump sum. So now let's see. So the second option says it receives monthly payments for 25 years starting 1 month after retirement. Okay. So it says that for the first year, the amount of each monthly payment is 2,000. So we're talking about monthly payments in general, right? And they're saying that in the first year, monthly payments have already occurred, and each monthly payment is at 2,000. And for each subsequent year, remember there are 25 years in all. The monthly payments are 2% more than the monthly payments from the previous year. Okay, so um it says for each subsequent year, the monthly payments are 2% more than the monthly payments from the previous year using an annual nominal interest rate of 6% compounded monthly. The present value of the second option is P. Okay, so it says that for the first year, the amount of each monthly payment is 2,000, right? Which means that within 1 year, there has been 12 payments. And they're also saying that each subsequent year, the monthly payments are 2% more than the monthly payments from the previous year, right? So instead of just doing this incrementally monthly, let's just sum it up and make it yearly. So let's first, it says 2% more than the monthly payment. So that calls for an accumulation of monthly payments for the first year. So we're going to do 2000 S to the 12 payments. They gave us 6% compounded monthly. So let me get my calculator. So what we're going to do is we're going to do 6 divided by 12. We're going to get 0.5%. Now, then we want to build off from that because it says that monthly payments are 2% more than the monthly payments from the previous year. So let's solve this. So we're going to use our TVM. So 2,000 payments, 12 number of years. 0.5 as the interest rate, 0 as the present value, future value. Okay, so this is going to be 2, 4, 6, 7, 1 dot 12. Okay. Now for each year, monthly payments are 2% more than the monthly payments from the previous year. So we know that at time 2, building off from the accumulation of time 1, that it would consist of this amount times the growth rate of 2%. Another thing is that we would have to discount it back to the comparison date at time 1, which would be V. Now, this is going to be going on as to the same until it reaches to 25 when it's again building off from the accumulation times the growth rate of 1.02. It's always one less than the time that it's occurring at. So it's going to be to the 24th power, V to the 24. Yeah. Now this seems as if we need to use the geometric progression formula to solve for the present value. So what we're going to do is that we know that each of these time frames have the common notion of 24,671. So what we're going to do, we're going to do 24 1,671.12 times the first term, which is, well, what is the first term? We know that the first term, building off from the accumulation, it would be a growth rate of 1.02 times V. So let's just say that the first term is 1.02 V minus the first omitted term, it would be 1.02 to the 25 times V to the 25, right? If it were to continue on to times 26, and then 1 minus the common ratio, it would be 1.02 V throughout, right? Now let's solve this equation. But the thing is that we noticed that when we find the present value of this equation, it's gonna take us all back to the comparison date of time equals 1. But we wanna officially find the present value of this whole thing, so we're gonna also discount it back one more period to time 0, right? So this would be the whole equation that we are going to be focusing on. So, another thing is that not only do we have this equation that we're finding present value of, but we also accumulated 1 year to find that the monthly payments are going to equal this amount, which means that we will add it to the present value of this amount, also discounted by 1 year as well. So now this is our whole equation that we need to solve. Now the thing is that they're giving us 6% compounded monthly, but we're kind of now we compressed each monthly payment into fitting into the end of each year, and now we are discounting back the payments, not monthly but annually. So what we're going to do is that we're going to convert this monthly percentage rate into an annual effective. So what we're going to do is that we're going to do 6 monthly is 1.005 to the 12, set it equal to an annual rate. We're going to find the annual rate here. So what we're going to do is that we're going to do 1.005 to the 12, okay, and then minus 1. And so we're going to find out that the interest rate is 0.061677. Now what we're going to do here is that we're going to solve this. We're going to take this and we're going to discount all over here. So 1.02 times 0.066 to the negative 1. So it's going to be 0.960744. And then we're going to do minus 1.02 to the 25. 1.02 to the first part is going to be 0.960744, right? And then now we're going to do minus 1.02 to the 25. It's going to be 1.640605 times b to the 25, which is going to be 1.061677 to the negative 25. So this is going to be 0.3674464 in whole. Now we're going to put this over 1 minus, it's pretty much the same number that I got from here, 60744. Now we're going to solve this problem. So we're going to do 0.960744 minus 0.36744464, and we're gonna get 0.593296, and we're gonna put this whole thing over to 1 minus 0.960744, and we're gonna get 0.039256. Now we're going to divide both values. We get 0.593296 divided by 0.039256. And then we're going to get this 15.11355. Now we're going to multiply it by the common thing, common accumulation, times 24,671.12. And then once we do that, we're going to discount it back one period. So multiply that by 1.061677 to the negative 1. And then we're going to find out that the present value here is going to be equal to 351. 206.87. Woohoo! Now for this part, we're gonna do discount the accumulation that we got from this region. We're gonna discount it back one period. We're gonna do 24,671.12 times 1.061677 to the negative 1 power, which is going to be 23237.87743. Now we're going to add this, what we got here. We're going to do plus 351,206.87. We're going to get 374. We're going to get 374. 444.74 as the present value of the second option, which is P. Now we're going to compare to the lump sum, right? So it seems like more than equal to, well, it's definitely not equal to. So let's lump sum 374,500, and we have 374,444. So the lump sum option is definitely more than P, so we're going to get rid of A and B. Now, it seems here that if I were to subtract this from the lump sum, it's going to be by like around 55. So it's definitely, this is a stretch. This is definitely not true. So the lump sum amount is definitely around 60 more than this amount. Not necessarily exact, it's pretty approximate. I got 55.25 more, but 60 would be the best answer, so that's why it's D.